warmed up to a steady state within the room. The pathogen continued to be injected for the final hour of the experiment, but at that point the lights were turned on. And what we can see at the current exposure limits for far ultraviolet light, this led to about a 92% reduction compared to when the lights were turned on. For the newly announced limits for exposure from the American Conference of Governmental Industrial Hygienists, I think I got that correct, that leads to a greater than 99.9% reduction. And remember, the pathogen was still being injected into the room. So it's like running an experiment with, or having an infected person in the room continually for the 3 hours. And then the lights are turned off after hour 2.
As I mentioned, 6 to 12 air changes are recommended, but that has all to do with the infectiousness of the source. The greater the infectiousness, the greater number of air changes needed to produce the kind of protection we want. So essentially, more is better if it's feasible and affordable. It isn't feasible and affordable if you're moving bulk air and have to heat it and cool it and dehumidify it. Now, super spreaders account for most transmission of COVID. And now we're dealing with Omicron, which is more infectious than Delta, which is more infectious than the original strain. This concept of theoretical limits to how much ventilation or other forms of air disinfection can achieve is not new either. I published on this in 1991, saying that you don't get perfect air disinfection because of this target theory issue. You're always removing a fraction of what's left. You can't get to zero. Now we're talking about far UVC that Kenny and Ewan will be talking about in detail. And you see in some chamber studies that they'll talk about is that test organisms, you turn on the fixture and you get a plummet in the concentration of infectious particles, in this case, again, a bacteria.
So I'm a physicist, and so I wondered, could we take a physics-based approach, a different approach to this problem? And actually, that's where my physics background kicked into this story. So together with my physics colleagues, we realized there actually is a particular wavelength of ultraviolet light that should kill all bacteria, but should be safe for human exposure. And that wavelength is called far UVC light. And it's just the short wavelength part of the ultraviolet spectrum. So let's look to the future. So, I mean, I'm thrilled that we now have a completely new weapon, and actually I should say an inexpensive weapon, in our fight against superbugs. So, for example, I see far UVC lights in surgical theaters. I see far UVC lights in food preparation areas. And in terms of preventing the spread of viruses, I see far UVC lights in schools, preventing the spread of influenza, preventing the spread of measles. And I see far UVC lights in airports or airplanes, preventing the global spread of viruses like H1N1 virus.